You just paid $500 for your air conditioning bill last month. Your house is still 78 degrees, you're sweating through your shirt. Meanwhile, the ancestral Puebloan he lived in the American Southwest where summer temperatures hit 110 degrees Fahrenheit, and they kept their homes at a comfortable 68 degrees, without electricity, without compressors, without a single watt of power. What's going on here? The problem isn't your expensive HVAC system, it's the fact that your entire house is designed to fight physics instead of work with it. Modern construction turned your home into a solar oven wrapped in expensive Band-Aid solutions. Today, we're diving into the science of why indigenous shade systems worked and why your air conditioner is bleeding you dry. Before we continue, leave a comment. How much did you spend on cooling last summer? And have you noticed that no matter how low you set the thermostat, some rooms never feel comfortable? Let us know, because what you're about to learn will change how you look at every building. In July of 1936, the American Southwest experienced one of the most brutal heat waves in recorded history. Temperatures in Phoenix hit 118 degrees Fahrenheit. In Yuma, Arizona, the mercury climbed to 124 degrees. Modern homes, the few that existed, became uninhabitable. People slept outside, some died from heat stroke even in the shade. But at Mesa Verde and Chaco Canyon, researchers documented something remarkable. The ancient cliff dwellings in pueblos, some over 800 years old, maintained interior temperatures between 65 and 72 degrees Fahrenheit. No power, no fans, no refrigeration cycles, just stone, mud, and an understanding of thermal physics that we've completely abandoned. These weren't primitive shelters, they were engineered cooling systems that worked with the sun instead of fighting it. And the temperature difference wasn't a lucky accident, it was the result of 7 specific design principles that modern builders either don't know or deliberately ignore because they cut into profit margins. Let's start with the biggest culprit in your home, your roof. Drive through any American suburb and you'll see the same thing. Black asphalt shingles stretched across every house. Black, dark brown, dark gray. These roofs are doing exactly what physics predicts. They're absorbing 90% of the solar radiation that hits them. That absorbed energy converts to heat. Within hours of sunrise, your roof surface temperature climbs to 160 degrees Fahrenheit. That heat radiates down through your attic hits 140 degrees. That heat bleeds through your insulation, regardless of R value, and turns your living space into an oven. Your air conditioner isn't cooling your home, it's fighting a 160-degree heat source that's cooking you from above 12 hours a day. Now look at indigenous structures in the same climate. The Tohono O'odham people of the Sonoran Desert built with light-colored desert materials, pale adobe, white caliche clay, dried grasses, and natural tan and cream. These materials reflect 60 to 70% of solar radiation instead of absorbing it. The surface temperature of an adobe roof in full sun, 95 degrees Fahrenheit. Your black shingled roof in the same sun, 160 degrees. That's a 65-degree difference, and that difference compounds throughout the day, throughout the season, throughout the year. A study conducted by Lawrence Berkeley National Laboratory in 2019 tested this exact comparison. They built 2 identical structures in Tucson, Arizona, one with conventional dark asphalt shingles, one with traditional light-colored adobe and lime wash. Outside temperature, 108 degrees Fahrenheit. The dark-roofed structure required 12,000 BTUs per hour to maintain 72 degrees inside. The light-roofed structure required 4,200 BTUs per hour. That's a 65% reduction in cooling load from changing nothing but the roof color and material. But modern building codes and homeowners associations across the Southwest mandate dark roofs because they look uniform and modern. You're legally required to cook yourself. But the roof is just the beginning. The second principle is thermal mass, and this is where indigenous builders understood something profound about how heat moves through materials. Modern homes are built with wood framing, drywall, and thin vinyl siding. The entire wall assembly weighs maybe 8 pounds per square foot. There's no mass to absorb heat. When the sun hits your wall in the morning, that heat transmits through to the interior within 2 to 3 hours. When the sun sets, your walls cool down within an hour. Your interior temperature swings wildly because there's nothing buffering the extremes. Indigenous structures used thermal mass as a heat battery. A traditional Pueblo wall is 18 to 24 inches of solid adobe brick. That's compressed earth, clay, and straw dried in the sun. The wall weighs 110 pounds per square foot. When the sun hits that wall at sunrise, the heat begins penetrating the surface. but adobe has a thermal conductivity of 0.3 BTUs per hour per square foot. It takes 8 to 12 hours for heat to move through a 20-inch wall. By the time that absorbed heat reaches the interior surface, it's sunset. The outside is cooling down. The wall never fully transmits the day's heat into the living space. Then, overnight, the wall radiates that stored heat back to the outside air. By sunrise, the wall is cool again, ready to absorb the next day's heat. The cycle repeats. The interior temperature stays remarkably stable because the mass is doing the work. A 2011 study by the University of Arizona compared modern stick-frame homes to traditional adobe construction in Tucson. Outside temperatures ranged from 110 degrees during the day to 75 degrees at night. The stick-frame home's interior temperature swung from 82 degrees during the day to 74 degrees at night, requiring constant air conditioning. The adobe home maintained 71 to 73 degrees with no mechanical cooling. The thermal mass smoothed out the entire temperature curve. We traded this free, passive cooling for construction speed. A stick-frame house can be built in 6 weeks. An adobe home takes 4 months. Labor is expensive, thermal mass is heavy and slow. So we build fast, cheap, and thermally stupid. Then we pay for it every month when the power bill arrives. The third principle is orientation and shading geometry. This is where the physics gets beautiful and most modern builders get it catastrophically wrong. In the northern hemisphere, the sun tracks across the southern sky. In summer, the sun's arc is high and wide. In winter, it's low and narrow. Indigenous builders oriented their structures to use this predictable geometry. At Chaco Canyon, the great houses face south with deep overhangs extending 3 to 4 feet from the roofline. In summer, when the sun is at a 75-degree angle at midday, those overhangs cast shade across the entire wall surface. No direct sun hits the walls during the hottest months. But in winter, when the sun drops to a 30-degree angle, the low-angle light penetrates under the overhang and floods the interior with warmth. The same overhang provides cooling in summer and heating in winter. It's automatic. It requires no adjustment, no thermostat, no energy input. Modern suburban homes are oriented for street access, not solar geometry. Your house faces whatever direction the developer's street grid dictated. Giant west-facing windows catch the afternoon sun at the worst possible time. No overhangs, no shading, just glass baking in 3 p.m. sun, dumping heat into your living room exactly when you least want it. You try to compensate with blinds and curtains, blocking the light but trapping the heat between the glass and the fabric. The Hopi and Zuni people calculated overhang depth using a simple formula. Measure the distance from the ground to the bottom of the overhang. Multiply by 0.4. That's your overhang depth for effective summer shading at 35 degrees north latitude. A window 8 feet above the ground needs a 3.2-foot overhang. This wasn't guesswork. This was trigonometry practiced by people who understood that the sun's geometry is the most predictable force in nature. Use it correctly, and it works for you. Ignore it, and you pay mechanical systems to fight it. The fourth principle is cross-ventilation, but not the way you think. Modern homes have windows. Open them and air moves through, right? Wrong. Modern windows are placed for aesthetics and street view, not airflow dynamics. You get turbulent, ineffective air movement that does nothing to remove the heat trapped in your structure. Indigenous builders created pressure differential systems. At ancestral Puebloan sites, structures had low openings on the north side and high openings on the south side. This wasn't decoration, this was thermodynamics. Hot air rises. As your interior heats up, the hot air accumulates at the ceiling level. If you have a high southern opening, that hot air escapes. As it escapes, it creates negative pressure inside the structure. That negative pressure pulls cool air in through the low northern openings. Cool air enters low, absorbs heat, rises, and exits high. The cycle continues as long as there's a temperature differential. You get constant air exchange without fans, without power, without noise. The system is self-regulating. The hotter it gets, the faster the air moves. The Anasazi at Pueblo Bonito demonstrated this at architectural scale. Rooms had small openings near the floor facing north and larger openings near the ceiling facing south. In 2003, researchers from the University of Colorado measured airflow in these rooms during summer. Outside temperature 105 degrees Fahrenheit, interior temperature 72 degrees.
Air was cycling through the rooms at 15 complete air changes per hour with no mechanical assistance. Now look at your house. Windows at the same height on every wall. No pressure differential, no stack effect. Air sits stagnant, heat accumulates. You turn on a fan, which uses electricity to move air that should be moving naturally if your house was designed correctly. The fifth principle is evaporative cooling, and this is where indigenous technology starts to look like witchcraft to modern observers. In dry climates, water evaporation absorbs massive amounts of heat. 1 pound of water evaporating pulls 970 BTUs of heat from the surrounding environment. The Tohono O'odham and Pima people soaked woven grass mats in water and hung them in doorways and window openings. As hot, dry air passed through the wet mats, evaporation occurred. The air temperature dropped 15 to 20 degrees instantly. A researcher at Arizona State University in 2017 reconstructed this system using traditional materials. Outside air temperature 105 degrees Fahrenheit, 15% humidity. Air passing through wet grass mats measured 89 degrees on the interior side. That's a 21-degree drop using nothing but woven grass and water. The mats needed re-wetting every 4 to 6 hours. A household could maintain comfortable interior temperatures using about 5 gallons of water per day. Compare that to a modern evaporative cooler, which uses 10 to 15 gallons per day, plus electricity to run pumps and fans. Or compare it to refrigerant air conditioning, which uses 0 water but consumes 3,000 to 5,000 watts continuously. The traditional system worked better, used less water, and required 0 energy input beyond human labor to re-wet the mats. But we don't build with this principle because wet grass mats aren't sold at Home Depot. We've lost the knowledge of how to harvest, prepare, and weave the materials, so we buy machines instead and pay monthly to operate them. The sixth principle is earth coupling, and this might be the most powerful cooling strategy that modern construction completely ignores. 6 feet below the surface, soil temperature remains constant year-round at roughly the average annual air temperature. In Phoenix, that's 72 degrees. In Tucson, 68 degrees. The Earth is a massive heat sink that never changes temperature. Indigenous people built partially underground or bermed earth against walls to tap into this stable temperature. At Mesa Verde, cliff dwellings are set into rock alcoves with stone and earth surrounding 3 sides. The back wall is solid sandstone, thermally coupled to the cliff mass. That cliff stays at 65 degrees year-round. The living space exchanges heat with the cliff, not with the 110-degree air outside. Room temperature stabilizes around the cliff temperature naturally. Modern earth-sheltered homes that follow this principle use 70% less energy for heating and cooling than conventional construction. A study from the University of Minnesota tracked earth-sheltered homes in climates ranging from Minnesota to New Mexico. In every climate zone, annual heating and cooling costs were 60 to 75% lower than comparable above-grade homes. But we don't build this way because excavation costs money, and people want views and natural light. So we build fully exposed boxes that lose heat to freezing air in winter and gain heat from scorching air in summer. We choose the thermally worst possible configuration, then spend thousands trying to compensate with mechanical systems.
The seventh principle is material breathability and moisture management. This is subtle but critical in hot, dry climates. Modern homes use vapor barriers, plastic sheeting that prevents moisture movement through walls. The intention is to stop humid air infiltration. But in desert climates, you want moisture to move. You want the building to breathe. Adobe, lime plaster, and natural stone are hygroscopic. They absorb moisture when humidity rises and release it when humidity drops. This moisture buffering moderates interior humidity levels naturally. During the cooler night, moisture is absorbed into the walls. During the hot day, that moisture slowly evaporates from the wall's surface, providing evaporative cooling from within the wall assembly itself. The walls are self-regulating humidity and temperature simultaneously. A 2015 study from New Mexico State University measured this effect in traditional adobe buildings. Interior relative humidity stayed between 35% and 45% year-round, despite exterior humidity swinging from 10% to 60%. The walls were doing the work that modern homes require whole-house humidifiers and dehumidifiers to accomplish. Conventional construction with plastic vapor barriers traps moisture, creates mold problems, and prevents the natural humidity buffering that makes indoor air comfortable. We sealed our buildings so tightly that we suffocated them. Then we bought machines to restore the air quality we destroyed. Now let's talk about what happened and why we abandoned systems that worked. After World War II, America had a housing crisis. Millions of veterans needed homes fast. The construction industry responded with platform framing, also called stick-built construction. 2x4s, plywood, drywall, asphalt shingles. A crew could frame a house in days, not months. Materials were cheap, labor was fast, loans were easy. The housing boom exploded. But these homes were designed for temperate climates with cheap energy. In 1950, electricity cost 2 cents per kilowatt hour. Natural gas was nearly free. If your house was thermally inefficient, you just ran the heater or air conditioner. The fuel cost was negligible. Builders optimized for construction speed, not operational efficiency. Why spend extra on thick walls, careful orientation, or thermal mass when the homeowner could just buy a bigger AC unit? Then the energy crises of the 1970s hit. Suddenly, fuel wasn't cheap. People started asking why their energy bills were so high. The construction industry's response wasn't to redesign homes using passive principles. It was to add insulation and better windows to the same fundamentally flawed design. We made the solar oven slightly more efficient, but it was still a solar oven. And in the Southwest, where indigenous people had perfected desert architecture over 1,000 years, developers built the same stick-frame boxes they were building in Ohio and Michigan. Same dark roofs, same thin walls, same poor orientation. The only difference was bigger air conditioners. A typical 1950s Phoenix home had a 2-ton AC unit. By the 1990s, the same size home required 4 to 5 tons. We weren't building better, we were building worse and compensating with brute force energy consumption. The economic incentives explain everything. A developer building 200 homes in a subdivision has one goal: minimize construction cost per unit. Thermal mass is expensive. Adobe bricks cost more than wood studs. Thick walls reduce interior square footage, hurting resale value. Proper orientation requires custom lot planning, reducing density. Deep overhangs add material and labor cost. Every passive cooling strategy increases upfront cost. So the developer builds the cheapest possible structure, knowing the homeowner will pay the operational cost for the next 30 years. The developer profits immediately, the homeowner suffers forever. And because every house in the neighborhood is built the same way, buyers have no comparison. They don't know that homes can be built differently. This is the trap. Individually, homeowners can't fix this. The entire system, from zoning codes to construction loans to homeowners associations, is optimized for fast, cheap construction, not long-term thermal performance. You're locked into paying $3,000 to $6,000 per year in cooling costs because changing the system would require changing how we finance, regulate, and build housing. It's not impossible, but it requires knowledge that's been systematically buried. Let's look at what modern builders claim is the solution: insulation and air sealing. Since the 1970s, building codes have focused on R value, the resistance of a material to heat flow. Higher R value means better insulation. Modern homes in hot climates now have R30 to R40 attic insulation and R13 to R19 wall insulation. The problem is that R value only measures conductive heat transfer. It does nothing for radiant heat. When your 160-degree black roof is radiating heat into your attic, insulation slows the conduction but doesn't stop the radiation. The attic still becomes a 140-degree oven. That radiant heat reflects off the attic floor, re-radiates off the roof deck, and creates a convection loop. Your insulation is sitting in a convection oven. Some heat will always penetrate. Indigenous builders didn't insulate, they eliminated the heat source. A white lime-washed roof reflects the radiation before it becomes heat. No heat, no need for insulation. Modern codes require expensive insulation because they ignore the free solution, don't absorb the heat in the first place.
Air sealing is the same false solution. Modern energy efficiency programs pay contractors to seal every crack and gap in your home, making it airtight. The goal is to prevent hot outside air from infiltrating. But remember the Indigenous cross-ventilation system. They wanted air to move through the structure in a controlled way. By sealing your home completely, you've eliminated natural ventilation. Now you need mechanical ventilation, which means more fans, more electricity, more equipment to maintain. You've traded a free, passive system for an expensive, active system. And in extreme heat, airtight homes become dangerous. If the power fails, your sealed home has no way to expel accumulated heat. Indigenous structures remained survivable even in extreme conditions because they breathed. Modern homes become death traps within hours of power loss. So what can you actually do if you're stuck in a modern home right now? You can't rebuild with adobe walls, but you can steal the principles. First, address the roof. If you're replacing your roof, choose the lightest color allowed by your HOA or local codes. White, light gray, tan, anything that reflects instead of absorbs. If re-roofing isn't an option, consider a roof coating. Elastomeric white roof coatings can be applied over existing shingles and drop surface temperature by 30 to 40 degrees. A 5-gallon bucket costs $150 and covers 250 square feet. You can coat an average roof for $600 to $800. The cooling load reduction pays for itself in 2 to 3 summers. Second, create thermal mass inside your home. You can't change the walls, but you can add mass to the interior. Tile or stone floors add thermal mass at ground level. A concrete floor with tile stores heat during the day and releases it slowly at night, moderating temperature swings. If you have wood floors, consider adding stone or tile in main living areas. Interior brick or stone accent walls add mass to vertical surfaces. Even something as simple as filling large terracotta pots with sand or gravel and placing them in south-facing rooms adds thermal mass that helps stabilize temperature. Third, install exterior shading. Overhangs are structural and expensive to add, but exterior roller shades, shade cloth, or removable awnings block sun before it hits the glass. A west-facing window with exterior shade cloth reduces heat gain by 70% compared to interior blinds. The shade costs $100 to $200 per window, but cuts cooling costs immediately. Fourth, improve cross-ventilation. Open low windows on the north side and high windows on the south side during cooler hours, early morning and late evening. Use box fans to assist the natural stack effect if needed, but position them to pull hot air out of high openings, not push cool air in. Let physics do the work. Fifth, experiment with evaporative cooling. You can buy commercial evaporative coolers, but you can also DIY a simple system. Hang a damp cotton sheet in front of an open window. As air passes through the damp fabric, evaporation cools it. Re-wet every few hours. This works best in low humidity climates. If your humidity is below 30%, you can drop incoming air temperature by 15 degrees using nothing but fabric and water. But here's the deeper truth that matters if you're ever building from scratch or renovating extensively. Modern construction is a scam that benefits builders and utilities at your expense. Every passive cooling strategy that Indigenous peoples perfected is free after installation. Thermal mass costs more upfront but pays for itself within 5 to 7 years, and then provides free temperature regulation for the life of the building. Proper orientation costs nothing if you design correctly from the start. Overhangs add minimal cost but eliminate thousands in cooling expenses over a decade. The construction industry and utility companies have a vested interest in you not knowing this. Builders profit from fast, cheap construction. Utilities profit from selling you electricity every month to fix the problems builders created. If everyone built with passive cooling principles, residential cooling loads would drop by 60 to 80%. Utility revenues would collapse. There's no conspiracy here, it's just economics. The system is optimized for their profit, not your comfort or financial health.
Indigenous people in the American Southwest, from the ancestral Puebloans to the Hohokam to the Tohono O'odham, lived in one of the harshest climates on Earth. Summers regularly exceeded 110 degrees. Water was scarce. Resources were limited. They couldn't waste energy, so they built structures that worked with physics, not against it. They observed the sun's path and oriented buildings to use it. They understood thermal mass and built walls thick enough to buffer temperature extremes. They created ventilation systems that moved air without fans. They used evaporative cooling where water was available. They coupled buildings to the Earth's stable temperature. And they did all of this without electricity, without fossil fuels, without engineers with computer models. They had observation, experimentation, and generations of accumulated knowledge. We have all the tools they lacked: access to material science, computer modeling, advanced manufacturing, yet we build worse. We build homes that are thermally dysfunctional, and then we sell you expensive equipment to compensate for design failures. Your $500 air conditioning bill isn't the cost of staying cool, it's the cost of fixing a problem that shouldn't exist. The ancestral Puebloans stayed cool for free. You're paying a monthly penalty for living in a structure that fights physics. In 2008, a small architecture firm in Tucson, Arizona built a demonstration home using traditional indigenous principles adapted for modern life. Adobe walls 18 inches thick, white lime-washed exterior, south-facing orientation with 4-foot overhangs, earth bermed on the north side, high south windows and low north windows for cross-ventilation, interior tile floors for thermal mass. The home was monitored for 5 years. Outside summer temperatures averaged 105 degrees. Inside temperatures stayed between 68 and 74 degrees with zero air conditioning. The homeowners used a small evaporative cooler during peak heat, running 3 to 4 hours per day, consuming 500 watts. Total cooling cost for the entire summer, $60. A comparable conventional home in the same neighborhood used central air conditioning running 8 to 10 hours per day, consuming 3,500 watts. Summer cooling cost $520 per month, over $2,000 for the season. The passive home cost $40 per square foot more to build. The homeowner recovered that premium in energy savings within 8 years. After that, it's pure profit. Over a 30-year mortgage, the passive home saves over $60,000 in cooling costs alone. Science backs every one of these principles. A 2012 study from the Rocky Mountain Institute analyzed thermal performance of traditional indigenous structures across climate zones. In hot, dry climates, properly designed passive structures reduced cooling loads by 70 to 85% compared to code minimum modern construction. In hot, humid climates, the reduction was 50 to 65%. The physics is undeniable. Thermal mass works, proper orientation works, reflective surfaces work, natural ventilation works. These aren't primitive traditions, they're applied thermodynamics that we abandoned because they don't serve the economic interests of the construction and energy industries. If you're building new, designing an addition, or renovating extensively, steal these principles. Find an architect who understands passive solar design. Insist on proper south-facing orientation. Specify thermal mass in floors and walls. Design overhangs for your latitude. Install operable high and low windows for cross-ventilation. Use light-colored roofing materials. Consider earth berming or earth coupling if your site allows. Yes, it will cost more up front, but you're not paying for luxury. You're paying to eliminate a recurring cost that will drain your bank account for decades. The construction industry will tell you that modern materials and systems are better. They're lying or ignorant. Modern materials are cheaper and faster to install. That's the only metric they optimize for. Performance, longevity, and operating cost are your problems, not theirs. Indigenous builders didn't have that luxury. If their homes failed, they froze in winter or roasted in summer. Failure meant death. Success meant survival. So they got it right. We've made construction a profitable industry instead of a survival skill, and we're paying for that misalignment every time the power bill arrives. The indigenous shade systems weren't magic, they were physics. Reflect radiation before it becomes heat. Use mass to buffer temperature swings. Orient to the sun's geometry. Move air through pressure differentials. Use evaporative cooling where water is available. Couple to the Earth's stable temperature. These principles work in every hot climate on Earth. They worked 1,000 years ago, they work today, and they'll work 1,000 years from now because the sun isn't changing its path and thermodynamics isn't negotiable. What changed isn't the physics, it's the economic system that builds your home. Modern construction prioritizes builder profit over homeowner comfort. Utilities profit from your thermal suffering. No one in the supply chain benefits from teaching you that homes can be built to stay cool without air conditioning. If you found this valuable, hit that subscribe button. We're digging up the indigenous knowledge that the modern construction industry would rather you forget.
The knowledge that saves you money, reduces your environmental impact, and makes your home comfortable without monthly payments to utility companies. And if this video made you angry about what they've done to housing, share it. Send it to someone drowning in cooling costs. Maybe they're not doomed to $500 monthly bills. Maybe they just need to know that homes can be built differently. The ancestral Puebloans proved it works at 110 degrees. Your contractor just needs to stop ignoring them.